Last time we were talking about the intersection of two regular languages, and today I want to talk about the union. Actually, most of the work has already been done when we were talking about the intersections. So I would like to talk about, what about the union of regular languages? Is it regular? The answer is yes. It is. The union of two regular languages is regular, and I want to talk about how do you combine two DFAs into a single DFA which gives you the union. Actually, we again are going to use the product construction, the same construction from last time. It turns out the difference is only about which states are accepting versus rejecting. So we again use what the book calls the product construction. This is when you combine two DFAs by making pairs of states. This is what we spent most of our time last time doing. The only difference from the one which gives you the intersection is, I'll say we again use the product construction, but choose the accepting states differently. That's the difference. All right. The difference in this case, we need to accept anything accepted by the first machine or by the second machine. And the only difference from last time is that word or. Last time we were using the word and, all right? But because I'm talking about unions, it's or this time. Yep.
So does that mean that they don't even match in accepting states, or you're just taking all of them?
Did you say anything that matched?
Yeah, like, whereas, like, for the intersection, they both need to be...
Right, for the intersection, you take pairs in which both of the things in the pair were accepting in the original two machines. This one, it's just only one or the other has to be accepting. Yeah, that's right. That's how we're going to do it. I thought let's just try this by doing an example, because there's not a whole lot different about this versus last time. So here I give you two machines, and I'm going to name the states because that makes it easier to keep track of the pairs. In my opinion, it's pretty difficult to do this without giving names to the states. So here's my first DFA. 3 states in the first one, and the arrows go like this. All right, I think I put enough arrows everywhere for the first machine. And then the second one is also going to have 3 states, M2. I'll call these ones V, W, and X. Sorry, I meant to make state U also accepting, and state X is going to be accepting. And these ones, the arrows are like so. All right, those are my 2 DFAs. It's hard for me to say out loud what they are, but you can see the picture, I hope. All right. And your job, make a DFA which accepts the union of those 2 languages. So that would be L of M1 union L of M2. All right. And what we got to do is the same thing that we did last time. Make a new DFA using pairs. Like I said before, the only difference is deciding what are the accepting states. And we're going to choose the accepting states to be all pairs in which either the first thing is accepting or the second thing was accepting. All right, let's see if we can do it. I'm going to try to do this all on my page. So there are 3 states in each. Now, if I were to write all possible pairs, there would be 9 total possible states in this machine, although some of them are unreachable. So instead, I'm going to just start with the starting state, which would be S comma V. All right, you just take the 2 original starting states and combine them in a pair. And then I'm just going to see where can you get from there. The A from SV, if I do an A, where does that go to? Anyone remember how to do this? Yeah.
Goes to TX.
TX, yeah. Okay. And from SV, if I do B, you should look at from S, B goes to U, and from V, B goes to W. So from SV, I go to U comma W. So I'll write that down here, I guess, with a B. All right. And so on. Okay, how about the arrows from TX? If I do A from TX, A is a loop on T and also a loop on X. So actually A from TX goes back to TX. And B from TX, from T, B goes to S, and from X, B goes to V. So from TX, I go to SV, which I already wrote. So the B goes back like that. All right. And now we continue from UV. I guess there's nowhere else to go. From UV, if I do an A, I go, U goes to T, and V goes to X. So I go to TX if I do an A. Is that right?
Should it be UW?
It should have been UW here?
Yeah. Yeah.
Yes, it should have been UW. Thank you. It's easy to mess that up. I did this on my paper, and I checked like 3 times to make sure I got them all right. And I think I did it right on my paper. I had UW correctly on my paper. You don't care what's on my paper. All right, from UW, what happens if I do an A then? The U becomes a T, and the W becomes a W. So this goes to TW. I guess I'll put this over here with the A. It goes to TW. Okay, keep going. UW with a B. U goes to U again with a B. W goes to W again with a B. So UW with a B is the loop back to itself. And then from TW with A is T goes to T, W goes to W. So TW, the A is the loop. And from TW, a B goes to, T goes to S.
SW.
Yes, SW, which is a new state. This is not on my diagram yet. I'll put it over here, just so I don't have to scroll too much. All right, that was a B, right?
Yeah.
Okay, I hope I don't just keep getting new ones every time. SW with an A. S goes to T, W stays W, so SW with the A goes back to TW. And SW with a B, S goes to U, W stays a W. That goes to UW. And that's the end. Come on. A B here. And that's it. There are no more reachable states from the beginning. All right. I hope you all remember how to do that. A lot of opportunity to mess it up, but it's not that hard. I mean, you just got to be careful, which I sometimes am. All right. What about the accepting states? Remember I said the states down here should be ones which are accepting in the first coordinate or accepting in the second coordinate. So, looking at the 2 things in the pair. So S and U are both accepting. That means anything that starts with an S or a U is going to be accepting in this machine. So this one, sorry, that's the starting state. I forgot to write that. This one is accepting. Anything that starts with an S or a U is accepting, right? And also, X was accepting in the second machine, so anything with N, which ends with an X is accepting down here. Almost everything is accepting, all right? It's a very accepting DFA. The only one that's not is that TW, okay? If you think about it, the union, when you union things, it means it's going to be easier to be accepted, whereas the intersection is a narrower thing. Okay? So this is my DFA which accepts the union. Any questions about that? Once you know how to make the intersection one, it's basically the same thing for the union one. Yes?
Can you just explain why TX is accepting?
TX is accepting. Yeah. I want. Sorry.
Oh, because, oh wait, I'm sorry. Oh, X is the accepting state in M2?
Yes.
Okay,
You figured it out while I was choking.
okay.
Yeah, you take pairs in which either the first thing was an original accepting or the second thing. Or both, of course. All right. Great. Can we try just briefly to describe this from the formal point of view? Now, last time we wrote it formally and then went through a whole proof. I don't want to go through the proof. You could if you want to, but can we just describe this formally speaking? What exactly is that union machine? If we have M1 is Q sigma delta 1 Q0 F1, I'm going to write these just like last time, and M2 is, I'll use R this time, delta 2 R naught and F2. All right. Then what do we want for the machine which accepts the union? Well, all that's different is the accepting state. So I'll just say then we use, the rest of it was Q cross R for the first part. That means the set of states in my new machine is the set of all pairs from the two original machines. The alphabet is the same alphabet. The delta is a combination of the previous two deltas in the same way that we said last time. I don't think we need to get into that again, but it's the same from last time. The starting state, again, is the pair Q0, R0. And this is the interesting part. What goes here is the set of accepting states.
F1 times sigma and sigma times F2.
Say it again.
F1 cross sigma and sigma cross F2.
Okay, this is good. This is almost right what he said. Remember, to get the intersection, we did this, F1 cross F2. This is not the answer this time, but that gives you the intersection. That means the set of all things where the first thing is in F1 and the second thing is in F2. How do you write the set where the first thing is in F1 or the second thing is in F2? And remember that from your set theory class?
Is it U?
No, the union, if you just write F1 union F2, this means you make a set which consists of all those things taken together. It doesn't mean a pairs of things where the first part of the pair is in F1 or the second part of the pair is in F2. Actually, you do not remember that from your set theory class because there isn't a symbol for that. We don't ever write that. But what you have to do, you just have to write out. What we want is the first thing in F1, and the second thing could be anything, or the second thing in F2. And I think this is something like what you said a moment ago. Can you say that again?
F1 cross sigma and sigma cross F2.
Yeah, and? What do you mean?
Like plus.
How about union? This is almost right. Something is not quite right about this, but it's close. So I think what he's trying to say is, you got these ones wherein the first part of it is in F1 and the second can be anything. And then take those together, union, which means or, with this thing, which means the first part can be anything, but the second part has to be from F2. This is very close. Anybody see something slightly not right? Yeah.
Do you need star on the sigma?
This is a good guess, but that's not quite the issue. The sigma represents the alphabet, remember? What you should be talking about here are pairs of states. The first state from the first machine, the second state from the second machine. The sigma is not really appropriate for that. Anybody see what it should be? Yeah?
Could it be F1 and R and Q?
Yeah. You want R and Q here. So these two sigmas. This one should be R, which is the set of all states from the second machine. This one is Q. So what that means, if I were to translate, that's what should go in this blank spot that I wrote up there. I'll squeeze it in. It's not that. It's F1 cross R, union, Q cross F2. And the translation of that in words would be this F1 cross R means first thing in F1, the second is anything, and then or the second part means the first thing is anything, the second is in F2. All right. The R, I mean, I translated that as anything. R is just the set of all the states from the second machine. And Q is the set of all the states from the first machine. All right. So this is the proper way to write formalistically the machine made up of, the machine that's going to give you the union for the languages. All right. So all of this, I hope, makes sense. If you believe me so far, all of this constitutes a proof of this theorem, which I don't want to go through the details of the proof formally, but it says if L1 and L2 are regular, then L1 union L2 is regular. All right. Last time we wrote exactly the same thing, but with an intersection. And actually, the time before that, we had a similar thing, but with complements. If L is regular, then the complement of L is also regular. All right? Those are the three kind of basic set theory constructions that you can make. All right. Excellent. You might wonder about, what about, I don't know if you just remember things from your discrete math class. What about L1 minus L2, the difference between the two sets? This is another thing that you might think about. Actually, there's going to be a homework question next week related to that set. So I'm gonna leave that for the homework. Leave you in suspense about that one. Actually, that also is regular, but that's for you to think about. All right. This is all I want to say on this general topic for now. You know, these are referred to as closure properties for the regular languages, because it's all about if I start with some regular languages and combine them in a certain way, the result is still going to be regular. All right. I want to actually start today. We're going to start talking about another type of machine. The DFA was our first sort of major machine for the semester. We're going to talk about another one. But before that, I just wanted to talk about a language which is not regular. We've been talking over and over again about regular languages. They are languages which you can make using a DFA. Is there even anything that you can that is not the language of a DFA? Actually, there are some things. I don't know if you feel like DFAs, they could do anything, right? Actually, they can't do anything. Even there's some very simple languages that DFAs can't compute. So DFAs can't compute every possible language. And there are languages which are not regular. And I wanted to talk about just one example. You will see showing that a language is not regular is actually quite difficult. To show some language L is non-regular, that means it cannot possibly be the language of any DFA, no matter what the DFA looks like. So you have to somehow imagine any possible DFA and then demonstrate that that DFA cannot generate this language. To show some L is non-regular, you need to prove that no possible DFA can accept the language L. And I will just say, this is much harder than showing something is regular. Showing something is regular, all you have to do is write down an example of a DFA that gives you that set. But showing something is not regular, you have to somehow argue that no possible DFA could give you that set, which is, generally speaking, much harder. I want to do just one example to give you a feel for what it involves, and this is something we're going to come back to later on with some more fancy techniques to show that languages are non-regular. But I have one, this is actually the simplest example that we're going to talk about of a non-regular language. Here is an example of a language which you cannot ever be the language of a DFA. It's this. All right. A to the n, b to the n. We're going to see this example a lot because, like I said, this is the the standard example, the simplest example of a non-regular language. All right, this is all things. What's important here is the n there is the same both times. So it's all A's followed by the same number of B's. All right. And it's this issue about the same number that a DFA has a real hard time with. And I want to see if we can prove that this is not a regular language. You basically have to prove this by contradiction. You imagine that there was a DFA which had this as the language, and then you somehow derive a contradiction from that. So I'm going to say, maybe I'll write this as like a little theorem. L is not a regular language. All right, and we're going to do proof by contradiction. For the sake of a contradiction, I'm going to assume that it is a regular language. Assume we have a DFA. And I'm going to name the parts of it, although we're not going to get too fancy with the formalism here, but just so that I can talk about the ingredients of the DFA. It's this, right? Let's assume we have a DFA M with the language of M is that L, A to the N, B to the N, all right? And somehow we need to derive a contradiction from that, all right? Here's what I want to do. Just because I know how this proof is going to go, this is not an obvious thing to do, but if you think about this for a while, what I want to consider is just this, delta star of Q0 and A to the I for various I. All right? Just imagine, we don't have a diagram for this machine because in fact, the machine cannot exist, but we don't have much to go on. But let's just imagine we did have a machine. What I'm talking about here is I'm going to consider just where does it end up after you do A bunch of times. You do A once, you do A twice. For various different powers on that A, where is it going to end up? Here's what I would like to say. These cannot all be different for various I. Can anybody feel like they agree with me? They cannot all be different. Anybody agree? Why can't they all be different? Yeah? Yeah, because it's a DFA. It has only finitely many states, and this I can be anything, right? And so for various I, where I could be any number, they're going to have to repeat. Like a lot, actually. They can't all be different. So I'm going to say, consider this for various I. These can't all be different. Because, really, it's because Q is finite. And that's part of the definition of a DFA, is that the Q has to be finite. That's what the F means. All right? I'm all about the F. These can't all be different because Q is finite. So what that means is we must have delta star of Q0 and AI is equal to delta star of Q0 and AJ for some I not the same as J. All right? They can't all be different, which means there has to be at least two of them that match up. In fact, infinitely many of them have to match up, but two is good enough for me. They can't all be different, so there has to be two that are matching. And now I would like to consider what happens if I follow the string. So I was just doing A to the I. Now let's do B to the I right after that. What this means is then we'll have delta star of Q naught A to the I, B to the I must be the same as delta star of Q naught A to the J, B to the I. That's because I said after you do a to the I and a to the j end up at the same place. And if you immediately follow both of those with b to the I, I'm doing I both times here, then they still end up at the same place because they were at the same place after you did the a part, and then you're doing the same stuff after that. They still are going to end up at the same place after that. All right? And actually, this is a contradiction because the one on the left, this one, this is in L, all right? Sorry, I mean the string right there. A to the I, B to the I is in L. Because L, remember, was the language of all A to the N, B to the N, where it has the same exponent, right? But the one on the right side is not in L, and this is the contradiction. The one on the right side is not in L because those two exponents are different in the second one. But we're saying actually that the two sides are equal, all right? That's not allowed. So this machine, if it accepts a to the I, b to the I, it must also accept, sorry, I'm off the bottom. It must also accept a to the I, b to the j, all right? And that's the problem, where j is not the same as I.
So
Yeah.
if the A's and B's are supposed to be the same number,
Yeah.
how do you end up with a different number of B's for the second example?
Yeah. The reason I said these are equal, it's because the states that you get match up once you do a to the I and a to the j on either side. That means no matter what you do after that, you'll get the same answer from both parts, because the a to the I and a to the j, they sort of meet up in the same place, and then from then on they're always going to be equal no matter what you follow them by. And
that's what you were saying earlier about how eventually you run out of states, so you have to.
Yeah, right. They're gonna, I mean, these a to the I, b to the i's, they can't always be different. They're gonna have to sort of collide with each other after a while. And this is the problem. So this machine, if it accepts a to the I, b to the I, it must also accept a to the I, b to the j. So, come on now. Stop. So the language of M cannot be just this, a to the n, b to the n. If you want to accept those things, you're gonna have to accept more than that. You can't just accept that set. All right. Really, all of this, it comes down to the finiteness. That was the crucial ingredient of this argument. But I also ended up doing this fairly, sorry if you're still writing. This step right here is what got it all started, right? And that was kind of a rabbit out of the hat sort of thing. Like, this is not a general method that you could use to show that some language in general is not regular. This proof that I did works specifically for this example. And if you had a slightly different example, you'd have to change the argument around. So I'm trying to give you the impression that, yeah, it is possible to have a non-regular language, but it's not really easy to demonstrate that a particular language is not regular. You have to really think it through, and if I gave a bunch of examples, you'd have to come up with a new strategy every time, which is not a great situation. Like I said, later on, like a couple weeks from now, we're going to actually talk about a general purpose approach to non-regular languages. But for now, I'm going to leave it at that. Any questions about that? There are non-regular languages, and they are a little hard to show that they are non-regular. I forgot to write tune. Got to put that. That's why they keep signing up for this class. All right. Let's go on to the next type of machine. So this is all we're going to say for now about DFAs. DFA, remember, stands for deterministic finite automaton. The next level machine, what we're going to do as we go throughout the class, we are going to be introducing machines of greater and greater complexity, or greater and greater capabilities. This type of machine is like a DFA, but it can do a little bit more stuff than that a DFA is not allowed to do. So this one is called the non-deterministic finite automata. Non-deterministic finite automaton. And this is called NFA. We don't put the D in there. N stands for non-deterministic. All right, the non-deterministic finite automaton. This is meant to be sort of like as similar as possible to a DFA, but changing just one little thing at a time, just so that we don't go. It's not completely different. It's actually very similar. The difference is in the determinism. This is non-deterministic, whereas the DFA was deterministic. The difference here is that the NFA can act non-deterministically. That's the longest word I've written all day, I think. What it means is that if you use the same string and it looks like a DFA, it has a starting state, but when you do this string, a DFA, there's only one way that it could go. An NFA has sort of several possible pathways that the string could travel through. So that's what we mean by non-deterministically. The same string can result in several different ending states where it ends up. The same state can result in different final states. All right. Let me just show you what an NFA typically looks like. It looks like a DFA, and you actually have to kind of look carefully to be able to tell the difference at all, but I think you will be able to see the difference immediately. Here is an NFA. All right, here we have two states and a bunch of arrows. What's so N about this FA? Yeah.
There are two B's in the first state.
Yeah, there are two outgoing B's from the first state. Actually, that is the entire difference. There are two outgoing B's from the first state. So, I will just point that out. Two outgoing B's. This is not allowed in a DFA. It is allowed in an NFA. And so, for example, if we do AB, if you start in the starting state and you do AB, there's actually it could end up in either state. You could do AB as just following this loop both times and end up in the starting state. Or you could do AB by following the loop once and then going across B and ending up in the accepting state. Yeah.
When we relate, how are we going to decide which path?
Yeah, so the definition I'm about to say, let me just finish writing what I was saying. If we do AB, we can end up in either state. All right. What does it mean then for a string to be accepted versus rejected? So the definition of accepted has to change a little bit. On an NFA, a string is accepted if any of its possible paths leads to an accepting state. So in this case, AB is accepted because it is possible to get to the accepting state by doing AB. Even if there are some other sort of dead ends, it is possible to accept AB. So a string is accepted if any of the possible final states are accepting. All right. So in that example here, this one that I drew, AB is accepted. Is anything rejected by this? Can anybody give an example of a string which is not accepted? A, yeah, just A is not accepted, right? There is no way to end up over here if all you did was A. In fact, any power of A, I think, is rejected. And maybe some other stuff too, but I would say anything like a to the n is rejected. Right? Maybe is anything else rejected? Anything that ends with an A, I guess, is rejected. Maybe that's it. Sometimes it can be difficult when you're looking at an NFA to say exactly what are the accepted strings. But. All right, great. That's an NFA. So let me say, here's another example. Well, let me just say an NFA can have any number of outgoing arrows for any letter, and I will just emphasize, even 0. Any number of outgoing arrows for each letter. This allows you actually to draw NFAs. In fact, in my own personal opinion, and probably you will come to agree with me over the next few weeks, drawing NFAs is actually a little easier. If I describe a language and say, hey, give me the NFA which makes this language, it's actually a little easier than DFAs. For example, here's a nice, very simple NFA. That is a legal NFA. There are no outgoing arrows from the second state, but that's okay. You can have any number of outgoing arrows. And I think once you learn to sort of read the bones a little bit, I think it's pretty easy to just look at that and say, what's the set of accepted strings? Anybody have a feeling about this? Anything that ends with a B. So when I look at this picture, I say, what you can do is you can do whatever you want over here, and then have a B at the end, and it'll be accepted, right? This is what that means. Right? This accepts any string that ends with a B. Accepts anything ending with a B. Right? I like that. And it rejects anything else. For example, yeah, question.
So what if you had like A, B, A? Where would the last A?
Yeah, A, B, A. You might say, I'm going to do A here and then B here, and then I get stuck. Then that doesn't count as being accepted if you're stuck. That means actually you can't do A, B, A that way, but you can do it this way, A, B, A. So the only way to end up anywhere with A, B, A will end you up here.
Okay.
So that counts as rejected or not accepted. Yeah.
So if you have extra letters, you can't go to B early. Like for ABA, you can't go A and then B to the
right. Yeah. If you sort of get stuck with letters remaining, then it doesn't count as accepted.
Okay.
Yeah. You have to actually read the whole string and stop in an accepting state. That means it's accepted. All right. It's actually quite easy to draw things in this style. For instance, on the homework, you had to do this this example, 0x0. Remember that one? Where x is anything on 0, 1 star. This is actually a lot easier to do with the NFA. You can make it look very much like the one that I just drew. It has to. This is any string which starts with a 0 and also ends with a 0. Anyone think you can draw the NFA that does that? I can do it in 3 states in a line. You want to see a 0 and then whatever, some other stuff, followed by another 0 at the very end. Anybody got an idea? Yeah?
You just have an outgoing arrow, so the 0 going in the middle.
Yep.
And then anything like 0 or 1 like moving back, and then a 0 going to the last one.
Yeah, perfect. And this is accepting. So I think it's, when you do this using a DFA, you need more than 3 states maybe. You have to, it's more complicated, right? This one I think is very easy to look at. When you look at such a picture and you ask yourself, what are the accepted strings? All you're looking at is, how can I possibly get here? And the answer is, well, you got to start with a 0. Then you could do some funny business if you want, but you got to finish up with a 0. That's it. Yeah.
Well, how do you know where the empty string?
The empty string means you just start here and immediately stop, and it's rejected.
So I guess to go off of that, how do you know where the end of the string is? Like if you were to be in the middle there, and then how do you know like when it would go into the strings?
I'm not sure I understand the
Is
question.
it just the fact that it's like possible for that to happen?
Yeah, it's what we're talking about is just that it is possible to read the string and end up here. If this was like, you know, for instance, this is accepted because it begins and ends with a 0. If you like imagine that you are the NFA and you can only see one letter at a time, you might say get here and be concerned that like I'm not sure, is this really end or not? Maybe that's what you were asking. I would say it's true. If you were really only looking one letter at a time, you would not know that this was supposed to be the last one. But I would just say, don't think like that. That's not, when you decide if this is accepted or not, we can see the whole thing, and so we know how to work it out. Yeah.
Can a machine use an NFA?
Can a machine use an NFA?
Because the machine will read ones at a time.
Yeah, I guess you could wonder, is it even like realistic for a real machine in the real world to do something, to behave in this way, right? Yeah, maybe this is related to that question. How could an actual machine ever actually behave like this? You could say, so one, describing it as non-deterministic, that word has the connotation of something random happening. And so you could imagine a machine like this as somehow, when it gets here, say, and it doesn't know what to do next, when it reads a 0, should I stay here or go over here? A machine in the real world, you could, I suppose, design to flip a coin and make a guess and then repeat that over and over again using randomness to see if it could, or maybe even not using randomness, just like make both choices one at a time and see if either one works out. This could also, I mean, if you wanted a crazier analogy, you could think of this as some kind of like a quantum machine, which rather than making specific binary choices every time, it is actually capable of sort of superimposing the states and doing them both at the same time. That is a realistic idea, although not very down to earth. Yeah.
So if we were like given that NFA and then asked like, is that string accepted? Instead of going through like individually, we would just say like, well, what's accepted by it? Just look at it as opposed to like going through each like 0 and 1.
Yeah, I mean, yes, I would say if this were asked to me, is that string accepted or not? I would look at the machine first and see if I could get some abstract idea of what things are and are not accepted, and then look at the string and say if it is or isn't. Yeah, it's less. It's harder to go through this letter by letter because you don't really know where to go from one step to the next. It's true. These are good questions. All right. I just want to do a couple more examples. We gotta. It's almost time to go here. For example, actually, my other examples are similar to what I was going to say. An NFA is often simpler. This is like that one I just did. I think as an NFA is simpler than if you tried to do it as a DFA, which you have to do on your homework. An NFA is also often simpler than a DFA for the same language. I thought maybe we'd do a specific example. How about on the alphabet A, B, I would like the language is all X such that the second to last letter is A. this is kind of a pain to do with the DFA, but much easier to do with the NFA. The second to last letter is A. Let's try, first of all, with the DFA, all right? I have sort of a starting state which is not accepting. If you see an A, what I need to keep track of is where the A's are. And this is going to be a DFA, but basically, if I see two A's, I should accept. This means what I want to actually give names to these states. Sorry, I made them too small. This one, I'm going to say the A is last. Like if you've arrived in this state, it means the last letter that you saw was an A. And now if you see another A, this means AA is last. And this should be accepting because the second to last letter is A. Or if you saw a B here, it should also be accepting, but that means AB is last at the end, right? The end of the string at that point is AB. And then where else do the rest of my arrows go? Because this is a DFA, I need a bunch more arrows. If the last thing was AA and I see another A, then it's still true that the last two letters is still AA. Whereas if last two letters are AA and I see a B, then actually I go down to this state because now the last two letters are AB. So I put a B here. And then from here, if it says AB and you see another A, then I can go back up to this one because A would be the last thing. And if I see a B, then I'm sort of back to square one. This is kind of a tricky DFA, but that is a DFA which gives you this language when the second to last letter is an A. What about an NFA? So that's a DFA. How about an NFA to do the same thing? This is easier, in my opinion, once you get used to it. Yep?
For the starting state of the DFA,
Yes.
would we need to show a B then since it's a DFA?
Oh, yes, an outgoing B from the starting state. Yeah, thank you. Where should it go? Yeah, this should just loop back to itself. This state here basically represents the end of the string is not A. So it's B or the empty string. Yeah.
If you were to write it formally for the alphabet, would you put a star since it could be anything?
No. Formally, you would say sigma is AB. The alphabet, sigma, is always just a set of individual letters. You put the star if you wanted to describe, like so I didn't put it right here, but it's kind of implicitly. If you wanted to be more detailed here, I would say X in AB star. The star should go there because X is any string using A's and B's. Yeah. Or if you called it sigma, you could say X is in sigma star. Yeah, that star is a little pesky. Can I just write this NFA? I know it's about time to go, but the second to last letter is A. Anybody feel like you can make it happen? Yeah. What do you say?
The beginning stuff is
Yeah.
not accepting.
And
then it has a loop of A, B, C.
Okay. A's and B's.
Then it points to another unaccepting.
Yeah.
A.
With an A. Yeah. Okay.
Then that points to an accepting state. Like
Yeah. Excellent. So, how you interpret this is you can start off and do whatever you want for a while, but eventually you got to settle down, do A, and then one more thing, and then it should be accepted. All right? And this means the second to last letter is a A, and the very last letter is either A or B, doesn't matter. Great. So we'll have a lot more NFAs next time.